Welcome to the second part of Unit 5, and in this part and in the third part, I'm going to be working a group of examples for 2D projectile motion. As a reminder, here is the approach for these problems. You want to draw a picture. You want to write your grocery list. You need to look at the equations in order to determine the best way to find the information you want. And as reminders, don't forget things that are helpful, like vertical velocity is 0 at the top. And if you have symmetry, exploit it if you can. Okay, so on to the first example. And this is almost the easiest projectile motion question that could be asked. So we have a tiger that leaps horizontally from a 6.5 meter high rock at a speed of 3.5 meters per second. How far from the base of the rock will he land? Okay, so first things first. Draw a picture. And I always start my picture with my coordinate system. So this is my x equals 0 mark. This is my y equals 0 mark. And up here I have at 6.5 meters, my tiger jumping horizontally, which means V naught is strictly in the x direction, and we know it equals 3.5 meters per second. And then the tiger lands, say here, at our unknown x. Last piece we need for our picture is gravity, so there it is. Now we have to write our grocery list. Okay, so taking it little bit by little bit. He starts at a horizontal position of 0. Because we let it be that. He starts at a vertical position of 6.5 meters, and he lands on the ground at 0 meters. The horizontal distance is what we want to know. We know our initial velocity is only in x, so I can write that as 3.5 meters per second, and initial velocity in y is 0. Acceleration is only in the y direction, and it is gravity downwards, so that is negative 9.8 meters per second squared in this coordinate system. And in the x direction, it is 0, so put that in. Because the acceleration in the x direction is 0, I can automatically fill in that my horizontal velocity is constant, so that allows me to fill in Vx. Okay, so at this point, I look at my equations and I will write out the main pieces that we need to think about here, but I'm not going to write it out on all of them. So in the x direction, we only have this one left because the acceleration is 0. And that sends the other two possible horizontal equations to just telling us that the horizontal velocity is constant. In the y direction, we have 3 equations still. Okay, I'm having problems down there because of my computer, so we'll go over here. Okay, I want to know horizontal position, so I have to use this equation. But in order to use this equation, I need to know time, which means I'm now going to go look at my vertical information, my other 3 equations, to try to find an easy way to get the value of time. I have the y equals y naught equation. That involves time. And you might be tempted to shy away from that one. That one's actually the easiest one to use because it involves time and it doesn't involve the vertical velocity component, Vy. So this is where we're going to go. As an alternate, if you want to shy away from this one because you realize this is the scenario that leads to quadratic formula and you'd rather avoid quadratic formula, though it actually doesn't come up here, you could use this equation to find Vy and then use this one to find time, an alternate. Okay, so I want to know x. In order to find x, I have to find t. So let's find t. Okay, so to find t, I'm going to start with my y equation. And now I'm going to plug in the numbers off of my grocery list. So 0 meters equals 6.5 meters plus 0 meters per second times my unknown time plus 1/2 of negative 9.8 meters per second squared t squared. So this goes away because it's multiplied by 0. I'm going to take 9.8 divide by 2 and get 4.9. And then I'm going to move the whole thing to the other side. So I get 4.9 meters per second squared. T squared equals 6.5 meters. So t squared equals 6.5 over 4.9 with units of 1 over second squared. And if you multiply that out, that becomes 1.331. Oop, I have the units wrong. Not 1 over second squared, units of second squared. So units still of second squared, taking the square root, I get t equals 1.15 seconds. Okay, so I now know how long the tiger is in the air. And now I can find the horizontal distance. And because I have lots of blank slides, I'm going to go to a new one and pull in my horizontal equation. So our initial horizontal position we let equal to 0. Our initial horizontal velocity was 3.5 meters per second. And we just found the time of 1.15 seconds. I don't really need to write out that acceleration term because there's a 0 there, but I like completeness, so there you go. If I take 3.5 times 1.15, I end up with 4.03 meters. And so that is the answer to the first question. Okay. Skipping through the blank slide, on to the next example. So we have a ball tossed off a 30-meter tall cliff at an angle of 15 degrees and a speed of 25 meters per second. And we want to know everything we can about the ball's landing. How long is it in the air? How far away from the cliff does it land? And at what speed is it moving right before it lands? Okay, so first things first, draw a picture. So you can see my cliff. I'm letting the edge of the cliff be my y-axis. Here's my x-axis. And the ball is tossed off the cliff at an angle of 15 degrees. If it doesn't specify or there's no drawing, assume it's with respect to the positive x-axis at 25 meters per second. The initial height is 30 meters. Let the ground be 0. Let the initial position be 0 in the x direction. And this thing's going to fly through the air and land somewhere over here, which I want to know lots of things about this landing spot. Okay. Now, the next step is to write the grocery list. So let's start thinking about our grocery list. forgot to put gravity into my drawing. There it is. Okay, acceleration is negative 9.8 meters per second squared. Downward in the y direction only. Horizontal acceleration is 0. Initial vertical position is 30 meters. Final vertical position is 0 meters. Initial horizontal position is 0 meters. Final horizontal position is one of the things we want to know. Time is one of the things we want to know. Vx and Vy are things we want to know. V naught x and V naught y, we don't know at this point, but we have the information to find them. And to find them, I'm going to draw myself a pretty little triangle. The hypotenuse is V naught. The angle is the 15 degrees. And then I have the horizontal and vertical components. I see that the x component is on the side adjacent to the angle, so V naught x is going to be 25 meters per second times the cosine of 15 degrees. And if you multiply that all out, you get 24.15 meters per second. Similarly, V naught y will be 25 meters per second times the sine of 15 degrees because it's on the side opposite. And that equals 6.47 meters per second. So I can plug this information in now. And that was 24.15. I can also say, hey, look, horizontal acceleration is 0. Therefore, I can answer this question already. What is the x component of the final velocity? It's 24.15 meters per second because horizontal velocity has to be constant. Okay, so now, taking this piece by piece. The first question, part A, asks, how long? How long is it in the air? So it's asking me to find time. Okay. I want to know time. Well, in the horizontal direction, the only equation I have is the one that goes x equals x naught plus v naught xt. And that involves both x and t, which I don't know. So the horizontal information is not beneficial to me. However, the vertical information does give me the information I want. Regrettably, the easiest way through that is using the y equals y naught equation, and it leads to quadratic formula. Okay. So plugging in 0 meters equals 30 meters plus 6.47 meters per second times t plus 1/2 of negative 9.8 meters per second squared t squared. So now I'm setting up for quadratic formula. So I'll make a little note of that. I can identify the coefficients I need for the quadratic formula. A is the coefficient of the squared term, so that's negative 9.8 divided by 2, which is negative 4.9. B is the coefficient of the linear term, so the one that's proportional to t, so that's 6.47. And C is the coefficient of the term that doesn't have a t, so it's 30 meters. And if I take and plug this information into the quadratic formula, the positive root results in t equaling negative 1.9 seconds, and the negative root results in t equaling 3.22 seconds. So this is the answer that I want. Part B of this question asked, how far? Which means it wants to know, what's x? Where is it relative to the bottom of the cliff? How far away is it? Well, I only have one equation that involves x, so I'm going to make use of it. So our initial horizontal position we let be 0. The initial horizontal velocity component we found to be 24.15 meters per second. And we multiply it by the 3.22 seconds that we just found. And then, as I said, I like completeness, so I'm going to write out the acceleration term as well, but it's 0, so it doesn't really contribute. It doesn't contribute at all. If I take 24.15 meters per second and multiply by 3.22 seconds, I find that the ball lands 77.76 meters from the edge of the cliff. Okay, last part. The last part of this problem asks you for the speed. Okay, which means it wants to know v. Okay, well, what we can find easily are vx and vy. We already know that vx equals 24.15 meters per second. We argued that several slides ago based on the fact that the acceleration in the horizontal direction is 0. Vy, however, I still need to find. And the easiest way to find Vy is to use the Vy equals V naught y plus a sub yt formula, because I know everything there. And it's much simpler than the one that involves the squares of the velocities. So V naught y was 6.47 meters per second. And then I have to subtract off 9.8 meters per second squared times the time, which I found to be 3.22 seconds. And when you put all that together, you get Vy equals negative 25.09 meters per second. So we found the components of the final velocity. But this question isn't asking for the velocity components, it's asking for the speed. And by asking for the speed, what it really wants is the magnitude of the velocity vector. So to find that, I need to draw myself a pretty picture. So I have Vx going this way, I have Vy going downward, and V is on the hypotenuse of that triangle. So you can see, hopefully, that I can use Pythagorean theorem to find the magnitude. What is it? Negative 25.09 meters per second squared. So squaring and adding gives that v squared is 1,212.73 meters squared per second squared, which means v is the square root of all that, which is 34.82 meters per second. Okay. So now we know the final speed. It's moving at 34.82 meters per second right before it hits the ground. Okay. One thing that isn't asked for here is what is the angle that it's approaching the ground. And to find that, I would look for this angle, because if you think about the ground being here, the opposite interior angles are equal, so that makes sense. So if I want to find that angle, and remember this is an aside, I would use that the tangent of theta is the side opposite divided by the side adjacent. So I can plug in my numbers there, negative 25.09 meters per second divided by 24.15 meters per second, which gives me the tangent of theta is negative 1.04. I can then take the inverse tangent to find the value of theta, and I get it to be negative 46.09 degrees. And you might be wondering about that negative sign. Well, by convention, remember, angles that are measured from the x-axis counterclockwise are positive, and angles that are measured from the x-axis clockwise are negative. Our angle starts at the x-axis and heads downward, so that makes sense. This concludes the first 2 examples on 2D projectile motion. In the next video, we will work 2 additional examples of 2D projectile motion.